we've already met exponential functions, but there is a particular function, exponential function, that has the number e in it, and you may have come across the number e before. So we'll just introduce the number e, where it comes from, and then we'll talk about the exponential function. E, just like we have the number pi in mathematics, e is sometimes called the Euler's number. Euler was a 18th century Swiss mathematician, Leonhard Euler, and he came up with the concept or the number e. So it's sometimes called Euler's number. Okay, where did it come from? Say you had $1 invested at 100%. Nice to get that interest rate, but anyway, at 100%. So if it was invested at 100%, if it was compounded yearly, at the end of 1 year, you would have 1 multiplied by, now if it's at 100%, it'll be 1 plus 100% is, and it's over 1 year, so it'll be just 1. And so you'll have $2 left at the end, or at the end of 1 year if it was compounded yearly. If it was compounded monthly, the initial amount you had would be $1 times 1 plus, now it would be 100%, which is the number 1 over 12, or raised to the power of 12. All right, so that would be the interest rate per month. It would be 1 over 12 as a decimal, and it would compound 12 times, so monthly throughout the year, 12 months, so you'd have that. And you get 2.613. If it was compounded weekly, 1 times 1 plus weekly, you'd have 1 over 52, or raise the power of 52, and you get 2.6926. If it was daily, it'd be 1 times 1 plus 1 over 365, or raise the power of 365, and you get 2.7146, and so on. So if it was down to minutes, so every minute it compounded, it'd be 1 times 1 plus 1 over 365, that's how many days in a year, 24 hours, times 60, or raised to and we get 2.71828. That's a very good approximation to what Euler's number is. If it was done to infinity, so E equals the limit as n approaches infinity, so the bigger these numbers got, the closer it gets to Euler's number, 1 plus 1 on n, or raise the power of n. So you can see the pattern there. So as n gets very, very large, that number approximates to 2.71828. It keeps on going. So there's a little bit of background as to how we can come by Euler's number. That's a definition of what Euler's number is. It's the limit as n approaches infinity, so the bigger this number here gets, the closer we get to Euler's number, you can see what happens here. We're the number 1 there, number 12, 52, 365, very large number of minutes in a year, and so on. So this gives rise to the number e, which is sometimes called the exponential number or Euler's number. And it also gives rise to the exponential function. The exponential function looks a little bit like a equals a0 e to the kt. E is Euler's or the exponential number. A0 is the initial quantity. And t is a variable, and k, so we'll put t as a variable, the independent variable, and k is the growth rate. So this would give you the final amount, given that we have a growth rate, we have an initial amount, and A would be the amount that is remaining, or the amount that there is after time t. So an important concept here is that this would be, if k is positive, then we have exponential growth. If k is negative, so up here is negative, we have exponential. The word we use is decay. So we have growth and decay. So if up there is positive, time is always going to be positive, obviously. And k positive, we have growth. If k up here is negative, we have decay. A0 is the initial quantity that's present, whether it be some sort of radioactive decay. This will be the amount that's there at the start, and we can calculate the amount that's there at the end. It may be growth, where we've got population growth. So this is the initial population. We know what the growth rate is, which is k. We can actually calculate the future population. In that case, we'll have exponential growth. So there's an introduction into the exponential number, but also the exponential function.